The modern world is complex, yet beneath the surface of our interconnected, information-driven society lie the physical realities that underpin our very existence. In a world where everyone is on their phones and God knows what else, it is not surprising that the physical realities are often blurred out. But yet, these physical entities are the fundamental elements that enable us to produce the food we eat, generate energy, and build the structures that house us. Vaclav Smil, a distinguished scholar of energy studies, in his fascinating book, How the World Really Works, isolates four materials as the so-called four pillars of modern civilization: steel, concrete, plastics, and ammonia. And I was sold. They are not just merely components of our built environment, but they represent the very backbone of our civilization. At its core, steel is mostly made of iron, with a few other elements mixed in to give it all kinds of special properties. This journey begins with pig iron, also called crude iron, a product of blast furnaces that contains 95 to 97% iron. However, pig iron has a high carbon content, making it very brittle and less ductile, meaning it is not very stretchy. It also has lower tensile strength, which is the ability to withstand stress compared to bronze or brass. To turn pig iron into the strong, versatile steel we use every day, the carbon content is reduced. This process makes steel incredibly strong and durable. In fact, steel is much stronger than some of the hardest stones and most common metals. For instance, steel beams can bear loads 15 to 30 times heavier than granite. It is 7 times stronger than aluminum and nearly 4 times stronger than copper. Steel is also much harder, about 4 times harder than aluminum and 8 times harder than copper. Plus, it can withstand very high temperatures, only melting at about 1,425 degrees Celsius, compared to aluminum at 660 degrees Celsius and copper's 1,085 degrees Celsius. There are 4 main types of steel, each with its unique qualities. We have carbon steels, alloy steels, stainless steel, and tool steels. Carbon steels are the most common, and they are used in buildings, bridges, and cars. Alloy steels have other elements added to them to improve certain characteristics. Stainless steel, which doesn't rust by the way, is often used in kitchen appliances and medical equipment. Tool steels are so incredibly hard that they are often used to make tools that are used to cut other kinds of steels, for example. They are used for hand tools like chisels, hammers, wrenches, etc. Understanding these different types of steel and their properties helps us appreciate how this remarkable material shapes our world, making everything from skyscrapers to kitchen sinks possible. So, now, let's imagine a world without steel. The towering skyscrapers that define city skylines are absent, replaced by shorter, bulkier buildings made from weaker materials. Bridges that span vast rivers and connect cities are now unreliable and fragile. Cars, trains, and airplanes, which rely heavily on steel for their frames and engines, are either significantly less efficient or just non-existent altogether, making travel slow and cumbersome. Everyday life would feel drastically different. Your kitchen appliances, which are typically sleek and durable, are now clunky and prone to rust or wear. Tools and utensils made from less sturdy materials break easily, leading to frustration in accomplishing even simple tasks. The safety and efficiency of our infrastructure, be it roads, railways, and pipelines, are compromised, which will inevitably lead to frequent maintenance and accidents. Even the medical field would face its own challenges. Stainless steel instruments and equipment are crucial for surgeries and patient care. The reality is, without steel, our world would be much less advanced, much less connected, and much less efficient. Cement is the magic ingredient that makes concrete possible. This fine powder is produced by heating ground limestone and clay, shale, or even waste materials in massive kilns at temperatures of at least 1450 degrees Celsius. The intense heat transforms these raw materials into a substance called clinker, which is then ground into the fine powder that we all know as cement. When mixed with aggregates like sand and gravel, along with water, cement acts as the binding agent to form concrete. Concrete is everywhere. It's in the roads we drive on, the bridges we cross, our dams, and the buildings we live and work in. Modern cities, in essence, are built from concrete, and without cement, creating concrete on the scale needed to support our societies would be simply impossible. Back to our exercise. Now briefly, imagine a world without cement. Our cities would look drastically different, with less durable and more costly alternatives, struggling to meet the demands of modern construction. The convenience and safety we often take for granted in our built environment would simply be compromised. Plastics are everywhere. The versatility of plastics stems from their ability to be molded into virtually any shape you can think of, making them integral to countless aspects of modern life. The journey of plastics begins with hydrocarbon feedstocks found in crude oil and natural gas. Through a process called steam cracking, these hydrocarbons are heated to extremely high temperatures, breaking them down into simpler molecules such as ethylene and propylene. These primary monomers are then synthesized into the diverse array of plastics we use every day. There are two main types of plastics, each with unique properties and uses. Thermoplastics, which soften when heated and harden when cooled, make up the majority of global plastic production. Examples of thermoplastics include low and high density polyethylene, PE, commonly used in packaging and plastic bags, polypropylene, PP, found in car parts and bottle caps, and polyvinyl chloride, PVC, used in healthcare products like catheters, IV tubings, oxygen masks, PVC-coated mattress cover, to name but a few. On the other hand, thermoset plastics do not soften upon reheating and are used in products requiring high durability, such as electronics and furniture. How did we even get to plastics anyways? We can go from 1600 BCE, when Mesoamericans crafted objects from natural rubber, to the 19th century, where we had the discovery of polystyrene and the invention of packaging, which is a celluloid that marked the dawn of artificial plastics. The early 20th century saw breakthroughs with Bakelite, the first fully synthetic thermoset. Again, thermoset are plastics that do not soften upon reheating, and flexible PVC, propelling plastics into widespread use. The mid-century introduced nylon, Teflon, and PET, that is polyethylene terephthalate, completely transforming consumer goods and packaging. By the late 20th century, plastic bottles had largely replaced glass, and polymer banknotes emerged. Okay, so that's quite a ride. An abridged one, I suppose. But before I move on, I will leave you with this stat. Global production of plastics increased from a mere 20,000 tons in 1925 to an astonishing 370 million tons by 2019. If you are about to bring out your calculator, there is no need for that. That's over 18,000 times increase. Let's proceed. Okay, maybe we cut to the chase with this one. Without ammonia, about 50% of people alive today wouldn't be here. So what's up with ammonia? I suppose we all know this, but you can't assume much of anything these days. Ammonia is the primary ingredient in nitrogen fertilizers, which are essential for high-yield agriculture. Nitrogen is a must-have nutrient for plants. It's a key component of chlorophyll, the molecule plants use to convert sunlight into energy through photosynthesis. Nitrogen also plays a critical role in the biosynthesis of DNA and RNA, the molecules responsible for storing and transferring genetic information, and in building proteins. Although nitrogen is abundant in the atmosphere, plants can't use the nitrogen gas N2 found in the air. They need nitrogen in a reactive form, which only a few natural processes like nitrogen fixation by bacteria, can provide. Certain bacteria, such as rhizobium species, form nodules on the roots of legume plants. Within these nodules, the bacteria fix atmospheric nitrogen gas into ammonia or ammonium, which the plants can utilize. However, staple crops like rice and wheat can't fix nitrogen on their own, and they require an external nitrogen source. Before synthetic fertilizers became a thing, more on that in a minute, farmers had limited methods to add reactive nitrogen to the soil. They would do crop rotation with legumes. Farmers would grow a legume crop such as clover and then plow it under to enrich the soil with nitrogen. Or they could just use animal manure, which contains reactive nitrogen compounds. Needless to say, the traditional methods were labor-intensive and could not supply enough nitrogen to support the high-yield agriculture that is needed for a growing world population. However, as it always happens, there was a revolutionary discovery. In the early 20th century, scientists Fritz Haber and Carl Bosch developed a groundbreaking method to synthesize ammonia. Known as the Haber-Bosch process, this technique uses high pressure and a catalyst to combine nitrogen from the air with hydrogen. This innovation made it possible to produce reactive nitrogen in the quantities necessary for modern agriculture. The Green Revolution, which began in the 1960s, was a period of significant agricultural advancement. New high-yield varieties of wheat and rice were developed, but these crops required substantial amounts of nitrogen to reach their full potential. The Haber-Bosch process enabled the mass production of nitrogen fertilizers, which in turn supported these high-yield crops and led to a dramatic increase in global food production. So, again, at the risk of repeating myself, if not for ammonia, many of us would simply not exist today. I should also add that while about 80% of the ammonia produced worldwide is used for fertilizers, it has numerous other applications, such as production of nitric acid, used in the manufacturing of explosives, in rocket propellants, dyes, fibers, cleaners, and so on. If you have granted Vaclav Smil that the 4 pillars of civilizations are, as I have mentioned, then it goes without saying that fossil fuels run our world. Let's reel through the facts. Steel. The iron ore smelting process, a crucial step in steel making, relies heavily on coke, a carbon-rich material derived from coal. The energy used to power blast furnaces and other steel-making processes also comes primarily from fossil fuels. Concrete. Cement production, the core component of concrete, requires immense heat generated by burning fossil fuels, primarily coal dust, petroleum coke, and heavy fuel oil. Plastics. The synthesis of plastics begins with monomers, simple molecules derived from crude oil and natural gas. The process of converting these monomers into polymers also consumes large amounts of energy derived from fossil fuels. Ammonia. The Haber-Bosch process mentioned earlier is a prime example of fossil fuel dependence. Natural gas is both the source of hydrogen and the primary energy source for this synthesis reaction. There are 2 commentaries about this analysis that are quite warranted at this point. The first was made by Professor Smil in the book, "The Importance of Reducing Dependence on Fossil Fuel Cannot Be Overstated." However, many folks do not simply realize how deep we are in this fossil fuel world. It appears that decarbonization is going to be a long-term process due to the pervasive use of fossil fuels in modern society. There are significant changes in energy systems and infrastructure that just need to take place. Smil argues that fossil fuels will remain crucial for decades, especially in sectors like transportation and heavy industry, where alternatives are still developing. The second point is more obvious and perhaps only tangentially related to the topic at hand. Our success in solving important problems does not diminish their importance. The fact that we have solved issues like building bridges or producing food does not make them any less crucial to our survival. They are worth our attention, even if it means retracing our steps. In light of all this, it's clear that the very foundations of our modern civilization, steel, concrete, plastics, and ammonia are both marvels of human ingenuity, and they are also sources of profound dilemmas. We rely on these materials to feed billions, build cities that defy gravity, connect distant lands, and sustain a quality of life that would have been unimaginable mere centuries ago. Yet, as the systems thinker Daniel Schmachtenberger points out, our technological prowess doesn't exist in a vacuum. Each stride forward can set off a cascade of unintended consequences, rippling outward through the complex webs of ecology, economy, and society. The approach we ought to take is to understand that our world is not a series of isolated problems and solutions, but rather an interconnected matrix of systems that interact in both predictable and unpredictable ways. When we celebrate the achievements of the Haber-Bosch process and the gift of abundant food it provides us, for instance, we must also acknowledge its role in overtaxing soils, polluting waterways, and creating a high-stakes dependency on fossil fuels. Similarly, as we marvel at the skyscrapers and infrastructure made possible by steel and concrete, we must also contemplate the immense energy inputs and carbon emissions that have become so deeply embedded in their production. Our tools and processes, once hailed as solutions to scarcity and hardship, are now implicated in creating new forms of vulnerability. Plastics, once a symbol of modern convenience, have now metamorphosed into environmental hazards scattered across the globe, hinting at the fragile nature of our so-called progress. In fact, microplastics in recent studies have been found in human kidneys, livers, and even in brain tissues. The call to action here is not to abandon these materials outright, an impossibility given the scale of global dependence, as I stated earlier, but to re-envision how we produce, use, and recycle them. We need a more integrated form of problem solving, one that admits the immensely complex world we live in. This approach challenges us to think systemically, to ask how our attempts to solve one issue might generate others, and to design materials that don't simply end up as pollutants, but can re-enter ecological cycles. Moving towards such a paradigm requires far more than technological fixes. It demands new governance structures that foster transparency, cooperation, and long-term thinking. It necessitates an educational shift that equips future generations to navigate uncertainty, understand trade-offs, and anticipate outcomes over multiple generations rather than electoral cycles. As Daniel Schmachtenberger has written about, on a cultural level, it might mean reassessing our definition of progress itself. In the final analysis, recognizing the delicate interplay among these pillars of civilization compels us to question the notion that technology alone can deliver salvation.